Hello and welcome to part 2. This basically lecture, this covers all the MATLAB implementation of what we have learned in lecture 2 regarding resolution, grayscale, and the memory requirements of an image. As we have already learned that resolution represents details present in an image, and this is defined in terms of number of rows and columns. The more details we are representing inside an image, more beautiful image it will appear on screen, more sharper image will appear on screen. However, it will require more memory. Less resolution, basically it will start showing us degradation or distortion in our image on the screen. However, it will require less memory on the disk. So in order to demonstrate all these concepts practically, let us start with very simple and default image present in MATLAB. This is coins.image, and we can see the default resolution, the actual resolution. This is 246 by 300, and apparently this is a good quality image, and we can see that there are different coins present in image, and we can see size and blur, size and color and texture. All these things are quite visible. Now let us start seeing the impact of decreased resolution. If I'm going to decrease resolution by half, and let us see how does it appear on screen. In order to decrease resolution, you can do manual cropping, manual trimming of rows and columns, or you can use by default MATLAB function imresize. So I have used here imresize, and if I'm going to display a new image with reduced resolution, now we can see the quality of image. It has comparatively some degradation. The actual image having 246 by 300 versus downgraded or less resolution having 123 by 150, and we can see that there are some visual discrepancies, there are some visual problems being represented, being noted in this image. Although still it is quite evident that we do have circular image, we do have circular objects present inside this image, but still we can see at the boundaries that there are certain degradations or there are certain contouring effects because of the low resolution. Let us further validate. If I'm going to reduce the resolution further, maybe the new image is this time 74 by 90, and yes, this time it is much more evident. This is much more evident, and we can see original image versus downgraded or reduced resolution, low resolution image, and we can see that it has almost become impossible to identify the coins or the objects present. And just for validation, if I'm going to see one more possibility, and this time resolution is reduced to further 50 by 60. Original 246 by 300 versus 50 by 60, and we can see that yes, it is almost impossible to identify that there are some circular objects or there are like coins present inside this image. This is what the impact or the effect of the degradation or low resolution. As we keep on reducing the resolution of images, actually we are losing details, and it becomes challenging to interpret or to extract information from the image on visual appearance. Like we do have a lot of distortions present in this image. Now, in order to demonstrate that why these distortions have been introduced, why these distortions are there, we need to understand that when we are having more detail or more rows and columns or more pixels, those pixels will appear close to each other. Those pixels will appear close to each other, and as a result, we will have some meaningful interpretation or some meaningful information. Let us see randomly a new matrix, a new image, and just for the sake of understanding, this is 10 by 10. 10 rows, 10 columns, and we can see that all these 10 rows, 10 columns make up a total of 100 pixels, and these pixels are displayed within this window space, and at least we can have some correlation, we can have some meaningful information. Every pixel is occupying a small area. For example, this yellow pixel, blue pixel, dark pixel, bright yellow pixel, and all this. In contrast, if I'm going to have a low resolution image and being displayed in the same window, for example, this time we are having a 3 by 3 image. Now let us have a comparison between these two images. This one on the left hand side, this is 10 by 10 versus 3 by 3. These 10 by 10 means total 100 pixels accommodated within this same window space. 3 by 3 means total 9 pixels accommodated being displayed within the same space. As a result, every pixel will start occupying more space. The size of every pixel, horizontal and vertical size of every pixel will expand, and as a result, they will start occupying more space in order to make sure that window space is full. Therefore, we will have less information present in more space, and this is what distortion is. When we are having distortion, this is what basically distortion is, that pixels will be located far from each other. As a result, every pixel will occupy more space, and as a result, we will see degraded quality of image. In comparison, more pixels located close to each other, and as a result, we will be able to identify some meaningful information or meaningful trends. Now, although we have seen that when we are reducing image resolution, it leads to basically a distorted image at the end. We are having a bad quality image at the end. Now let us see whether is it possible to increase the resolution and have a good quality. Like basically we are trying to do the reverse. So in order to demonstrate this, let us start with this low quality image resolution 50 by 60, and now let us increase resolution maybe by 10 times. Let us increase resolution maybe by 5 times, and let us see whether we're going to get some meaningful information, whether we get some improvement in the image quality. In order to see this, let us do one more experimentation, and yes, here it is. Now when we are comparing, now this time the left side image resolution, this is 50 by 60. In comparison, right hand side, this is 250 by 300. What we are doing is we are trying to make use of this image, low resolution image, as an input image, and we are trying to increase the resolution of this low input image to get something at output. We can see that increasing the resolution, although it has resulted in some sort of quality improvement, and at least we can now identify that there are some circular objects present in image, but this increase in resolution, this is not potentially, like, it is not conveying us too much information. It is not potentially increasing the image quality as per our expectation, because the output image, although this is 250 by 300 resolution, but this is not having all that information which was actually present in the input image. So starting from a low resolution image and trying to increase resolution, it might improve an image to a certain extent, but please do not expect that we will be having all information which was available in the input image. Why? Because when we were reducing the resolution, actually we were losing some information at every step. So if we start with a low resolution image, this means we already have lost a lot of information from the image, and the information which has been lost, it cannot be reacquired, because when we are coming back from a low resolution image to a high resolution image, all newly inserted rows and columns, basically they will have similar behavior, they will have similar response, they will have similar behavior from whatever is present in the low resolution image. Whatever we do have present in the low resolution image, it will be copied multiple times in order to make a high resolution image. So if information or the information which already had been lost during the low resolution, it cannot be recovered, and as a result, or like this is the reason why the reconstructed high resolution image is not as good as it was the original image. After discussing the visual interpretation, let's talk about memory requirements. As we know very well that the reduced image resolution will require less memory, and high resolution image will require more memory. This is further demonstrated that I have stored those low resolution image and original image in memory, and then I'm trying to read out the memory requirements in the disk, and here it is. The original image occupies around 37 kilobyte of memory, whereas low resolution image, which was 50 by 60, now this is occupying only 1.94 KB. So this is one good reason why we normally adjust resolution, that maybe we want to adjust memory requirements, or maybe if you want to transmit via internet or online, you may consider reducing your resolution. However, it should not be reduced too much, because it will like lose the information with every step. Similarly, coming to the second part of the lecture, which was talking about the grayscale or the binary gray level values, or like the representation of image on screen using gray level values. So let us read that same input image and let us display that input image using two gray levels only for the first instance. We do remember from the original image that this is a coins image. It is having quite evident information. Now, what if we are displaying that same image using only two grayscales, only two gray level values, and this is what it will appear on screen. If I can show you, this is the same coins image, but that coin image has been displayed using only two gray level values, or the grayscale has been reduced to binary. Now we can see that reduced grayscale, it has resulted in loss of information, and we can see only two different behaviors, that there are some circular objects present in the image. What they are, not sure, because information has already been lost. Okay, now let us represent the same image, actual image, by using four gray levels. I'm going to increase gray level, and if I'm going to use four gray levels, now this time it is expected that now you can see that we have started seeing more information on screen. Four levels versus two levels. Two levels were displaying very limited information. In contrast, four levels, these are representing that at least we are having some circular objects and there are some inside texture present. In maybe these are coins or whatever. And instead of four levels, what if I'm going to use 8 levels for displaying image? And yes, now you can see in comparison with 2 levels, 4 levels, 8 levels are being used to display image, and yes, these are comparatively representing much more visual information on screen. Similarly, if I'm going to use 64 gray levels, it is quite expected that I will be able to represent actual image, and this is the case. Now 64 gray levels are being used in order to represent that coins image, and as a result it is quite evident that these coins are meaningful representation, circular coins, and all the internal embossment and all the structure is represented. We can keep on increasing. 128 levels, we can use 256 levels, and standard grayscale images are normally encoded or normally represented using 256 different gray levels. Right? So just for comparative purpose, we can see image represented using 2 gray levels, image represented using 4 gray levels versus image represented using 64 gray levels. This means the grayscale we're going to use, actually this defines the details. The higher or the stretched the grayscale, the larger the grayscale, more details will be represented visually on screen. The compressed or the smaller grayscale, less details will be displayed on the screen. Along with this visual interpretation, we can also see the impact of grayscale on images, on memory impact, memory requirement. So let us save two images, one the original image and one the binary conversion. The original image, which was using 256 gray levels, it was appearing very good coins image on screen, and the binary, which was using only 2 gray levels, and it was represented as a black and white image on screen. So if we are going to represent that, if we are going to save that in memory, let us save this, and then we're going to check out how does it works, and the memory requirement for original image versus binary image. Now we can see that original image, this is occupying almost 37 kilobyte of memory on disk, whereas binary image, this requires around 1.49 KB of memory on the disk. So this is very important, that the change in resolution leads to change in memory requisition, change in grayscale leads to change in memory requisition for digital image. So this is all about the MATLAB implementation or practical implementation of whatever the concepts we have discussed in lecture 2. Now in next lecture we will talk about pixel neighborhood, pixel connectivity, and all those concepts regarding to respectively with this regards to lecture number 3. So stay tuned and keep watching. Thank you very much.